ahead. The only thing I can say for that is we usually do a lot of group work during class, and although I felt like we were behind, we're actually right on schedule. So what we'll do today is actually go through, we'll talk about one topic that was in the online homework that I didn't cover because we're going to cover it really in depth next week. But I'll go ahead and introduce it, and so that you can kind of understand what the definitions are. And then we'll go through some acid-base reactions and just kind of practice for a while, go through what we've been doing and get more in depth and really look at the type of problems you'll have to do as we move forward. So the concept that the definition that we had was nucleophiles, electrophiles, and leaving groups. This was in the reaction mechanism section, so it's in that homework. We'll also look at it extensively when we get to substitution reactions. Nucleophiles, right, are nucleus loving. That's what the nucleophile means. They're going to be things with available electron density. So if you think about it, a nucleophile is a nucleus loving. Nucleus is positive, so therefore it's going to be negative. Often these are going to be electron rich. And the things we're really looking for are lone pairs, negative charges, and pi bonds. So lone pairs, if we look at water has a lone pair. It has an available electrons, right? That lone pair is available. It could react. So therefore, this is a nucleophile. If we looked at an alkoxide, here it's got lone pairs, but it also has a negative charge. Okay, that's going to be a nucleophile. And then if we look at something like an alkene or alkyne, right, that pi bond there makes this a nucleophile. So all of these are nucleophiles. Okay, for electrophiles, I use the abbreviation E+. Here, these are electron poor species. So things with an empty orbital. Things that are positive, and things that are partially positive. So if we look at the first one here, this boron is stable with only 3 bonds. So that means it's got an empty p orbital, right? Since it has an empty p orbital, this is an electrophile. This carbon only has 3 bonds. It's got a positive charge. It also means that it has a empty orbital, right? So this one's got a positive and its empty orbital. The positive kind of signifying that it's got an empty orbital. So therefore it's electrophilic. And then the last one, right, we have a dipole moment that goes towards the bromine. It's more electronegative than the carbon. So that gives me a partial positive, partial negative. Because it has that partial positive, that position is electrophilic. Okay. Yes. Even though the bromine has a partial negative. But the bromine doesn't actually have available electrons, right? So the bromine's not going to make another bond. So even though it has lone pairs, it does not behave as a nucleophile. So it's got lone pairs, but no available electrons, right? We don't have double bonded bromine, okay? That also brings up a good point, which is in the same molecule, you can have more than one thing. So let's take a look at that. So if we look at, change our color. This molecule can react several different ways. If we look at that bond, that's a nucleophile. If we look at that hydrogen potentially is electrophilic, or we could say acidic. And then this oxygen can make another double bond, so those electrons are available. So that position could be nucleophilic. So one of the things about nucleophilicity that we'll get to next week in depth is looking at electrophilic positions and nucleophilic positions versus just blankly calling something a nucleophile or electrophile. So if we had a molecule like this is a nucleophile. That position is electrophilic. It does not react with itself because of the relative electrophilicity and nucleophilicity of the two groups. So the way to think about this is that the nucleophile needs a stronger electrophile to react with, and the electrophile needs a stronger nucleophile to react with. So we have a mild electrophile and a mild nucleophile. They don't react. Some molecules may have strong and strong. In that case, we end up with a polymer. The molecules just react together. So you can have a nucleophile and electrophile within the same molecule that don't react with each other. The last group is leaving group. And it is the molecule that leaves, right? So stability after leaving is the most important part. So what kind of things make good leaving groups? Well, we'll get into this really in depth, but right now halides make really good leaving groups because bromine negative is stable, chlorine negative is stable, iodine negative is stable, right? All those groups are stable by themselves. Water is a great leaving group. That one may not make sense. I'll show you an example in a second. And groups with resonance, right? Resonance can help stabilize. So to show this, if we look, a nucleophile attacks with that electrophilic position, we would end up with nucleophile plus Br minus. Br minus is pretty stable, right? We all would have no problem sticking our hand in a solution of sodium bromide. It's not that much different than sodium chloride. It's not going to do anything to you. If we looked at a nucleophile in the second one, right, again, because of that positive charge and the fact that it's oxygen, that's going to make the position Here, electrophilic, so nucleophile attacks electrophile, leaving group leaves. And so that gives me now nucleophile attached here, plus water. So that's why I said water, alcohols, right? What we did was we protonated the alcohol in this case, and that gave us water as a leaving group, right? And water stable, so it leaves fine. The last one, again, if we look at nucleophile attacking the carbonyl, a nucleophile attacking the electrophilic carbon, lone pair, the electrons go back. And here I end up with, again, the new substitution plus this species, but I can take that oxygen negative and push it out to each of the other oxygens. So that makes this molecule stable, right? So I have resonance stabilization here. So all three of these are good leaving groups. All of them make the carbon that they're next to electrophilic, right? So therefore, they kind of go together. There are times when a leaving group will leave before a nucleophile comes in, and we'll get to that next week. But what was on the homework was being able to define these. So nucleophiles, right? You're looking for available electron density. That's why halides don't fall in the group of nucleophiles. They're not really available. They want their electrons. They're going to keep their electrons. Nobody's going to take their electrons, right? So think about the halides as a highly selfish versus nitrogen and oxygen lone pairs, which they don't mind sharing, right? And then electrophiles, we're looking for electron poor species. Obvious ones are positive charges. Partial positives, you got to look at your dipole moments, and then empty orbitals. Sometimes empty orbitals are hidden, like in boron and aluminum. And then if we look at leaving groups, right, leaving groups are just stable after they left. So if something is stable as itself, right, as a negative anion, then it's going to be fine. So whether that's bromine negative, the water, or in this case, the mesylate compound. Okay. Questions about identifying nucleophiles and electrophiles. Okay. And the caveat here is that nucleophiles and electrophiles usually have a position versus a whole molecule. Most of the examples you'll have at this point should be small molecules that really behave under one way, but you're going to get large molecules where you're going to have to identify the electrophilic position, and we'll spend some time on that next week. Okay, let's look at again let's look at some acid-base reactions. And let's look at the most acidic proton. So one of the things you're going to have to do is identify large molecules and identify the most acidic proton, right? Where, if this is going to react with a base, where is it most likely going to react? So let's take 30 seconds or so, and let's see, identify where the most acidic hydrogens are. And let's go ahead and rank them. And for this first one here, let me show you the hydrogens I want you to focus on. Okay, so if we look at these three, the thing that we can do and you should do is first think about their conjugate bases. So this is the conjugate base there on the bottom one. This is the conjugate base. Okay. Now, if we look at the atom on each one of these, which atoms are going to be more stable than the other ones? In general, the oxygen negatives, right, are going to be more stable than the nitrogen negatives. Right, and if I had carbon negatives in here, they would be lower, right? And since you notice I didn't highlight any of the carbon hydrogens. So in general, that would put the two oxygen negatives above the nitrogen negative. Now, the nitrogen negative does have the possibility of resonance. Right, so that potentially could stabilize us a little bit. But there's also a tell on this one. If I had this amide, which is the most acidic proton? The nitrogen hydrogen or the hydrogen over here? Well, this one you've actually seen in your chart. This one you haven't, right? So it turns out it's not very stable. That's not very acidic proton, partly because of the way the nitrogen is interacting with the carbonyl. Okay? So it's not one you see at the bottom. So your pKa values and the fact that it's nitrogen would say that this is probably third, which is correct. The other two, now what we're looking for is what's the difference between the two oxygens? So after atom, we look at resonance, right? And which one of these two is got the resonance? The bottom one, right? I can take this electron and I can delocalize it through the ring. This one is isolated. And at that point, because we have our atom, right, giving us the 3 over here, and we have resonance and isolated, I can think this one has the second most acidic, and then the one with resonance is the most acidic. And there's an acronym that a couple of one of the authors of organic textbooks uses, ARIO. So atom or atomic, right? Resonance, inductive, right? And then orbital. So orbital would be the difference between a carbon that's sp, a carbon that's sp2, and a carbon that's sp3, right? So, yes. No, it'd be most basic, but it wouldn't be acidic. It would have a pKa of about 35. Still, it's a nitrogen negative, so it's going to be less stable. So if you think about it, alcohols are about 15, 15.7, 16, right? So that's 16, but then we jump all the way to 35 for amines, right? And then we jump to 50, right? So that atom is a big difference. Where when we look at resonance, for a resonance, if you think about oxygen negative for an alcohol versus a acid, right? We're changing about 10 or 12, but we're not changing 20, right? So the resonance does have a big impact. And then if we look at inductive, there we're usually only talking about 3 to 5 pKa units. Okay. Yes. It would. So that would be another stabilization for that one. But the nitrogen can't actually. Okay. So the nitrogen is only delocalized to the carbonyl, where the oxygen negative could delocalize out to the carbonyl. Let's try another one of those. And I'm stuck on rings this morning. Okay, let's compare those three. It's always a good idea to draw the conjugate bases. You can do like I did, time saving, and just not show the entire molecule, just show the functional group, the important part. So if we're looking at these three conjugate bases, again, if we look at our atoms, right, we've got carbon negative, oxygen negative, and oxygen negative, right? So therefore the oxygen negatives are going to be more stable than the carbon negatives. Right? So right off of the bat, that's would put this one at 3. Right? Then do we have resonance anywhere? Now, sometimes whenever people see negatives on an alkene like this, there's a consideration, well, that one must have resonance. Let's look at the orbitals, right? So if I have a double bond species like this, right, and I have my hydrogen there, what's happening with my orbitals? Well, if we look at it, I've got my p orbitals going up and down, right? And then my hydrogen is actually in this sp2 orbital. What do you notice right there? Okay, let me blow it up. We got the p orbitals going above and below, and right here we've got our sp2. What's happening at the intersection? Well, that's a node, right? What happens at nodes? Is there any electron density? No, right? So anytime I have a node, that means that those two sides are not communicating. When I have a p orbital and an sp2, right, on the same carbon, what's happening? This negative is in an orbital that cannot communicate with this pi bond, right? So one of the things that you'll see is you'll think, well, it's a negative, there's a double bond. No, the negative has to actually be one away. If the negative is actually on the carbon, the problem is that that is orthogonal or in the node. So therefore there's no communication between that negative and the p orbital, okay? And so that is not delocalized. Right, so that is isolated. So then if we look at, so there's no resonance here, right? No resonance to the oxygen, no resonance on the carbon. So then inductive, do we see a position that could have inductive? Well, this one has a strong electronegative atom, right? Chlorine, your halides are the ones you want to watch for very closely for this. Oxygens and nitrogens also can have inductive effects, but your halides are the big powerhouses in this case. So chlorine's pulling electron density there, which is going to pull a little electron density there. And really, we have a distance problem, right? And usually what you see is inductive effects really drop off after 5 sigma bonds. But here we're really only dealing with 2. So it would have been higher if it had been at this position, but I still have an effect even if it's just in that beta position, that one away position, okay? So therefore, this inductive effect is going to stabilize that molecule, which then gives me, you know, this is going to be more stable than that. Okay. Questions about this one? Okay. Let's look at a similar idea. Now let's rank. The next set of questions are going to be very similar, because what you're doing is you're ranking okay. So now let's rank the acidity. Again, let's take 30 seconds or so. Think about this one. Okay, so if we draw the conjugate bases, right, we pull off the most acidic proton. This time I didn't label the protons, but hopefully as you do this more, you realize it's going to be a proton that is attached to the most electronegative atom, right? So oxygen is going to be a hydrogen attached to oxygen is more acidic than a nitrogen, the more acidic than the carbon. So if I have an oxygen hydrogen, that's going to be the most acidic than that molecule over a carbon hydrogen, right? So right off the bat, I'm ignoring my carbon hydrogens because the pKa values of those are much lower, right? Their stability as a carbon anion are much lower. So we have oxygen negative, nitrogen negative, oxygen negative. From that, can we decipher any ranking? Well, the nitrogen negative should be lower than the oxygen negatives, right? So I can put that one as 4. Then I have oxygen negative, oxygen negative, oxygen negative. Do we have resonance? Yes, we have 2 of those have resonance. So if this one is isolated and I have 2 that have resonance, then this one becomes the third one, third most acidic. Then between these 2, do we have any potential inductive effects? Well, this one looks like it might have an inductive effect, but that chlorine is far, far away, right? So we have 1, 2, 3, 4, 5, 4 bonds, right? That's pretty far. But remember that this has resonance. So I can delocalize that negative charge right there to that chlorine, which is going to increase that inductive effect, right? If these were all sigma bonds, inductive effect still has to go through the sigma bond. It is going through the sigma bond, but I've delocalized the negative charge to the carbon next to that electrophilic group. Electronegative group. Okay, so that means this is going to be more stable because of inductive. which makes this the most acidic and that then the second. Okay. Yes. The electron density? Yeah, so if we had this example, he's happy. If we had this example, right, now if we look at that, that gives us, he's not happy, right? And then if we delocalized, well, let's do it the other way. We can put these electrons into the ring. Right, which would destabilize that a little bit, right? So if this was in comparison with those, this would have a lower pKa than just the non-substituted. So it'd be less acidic. Okay, questions about this? In reverse, if that had been a positive, that methoxide could have stabilized it. And we'll see that later, really late this semester. Okay, questions about those? You want to do one more set? So let's look at these. Take a little time. Okay, so we end up with the set of conjugate bases. I'm going to go ahead and draw the resonance contributor for all of these, since they all have a resonance contributor. Okay, so if we look at these, right, um, looking at the top row, we have oxygen negative, oxygen negative, oxygen negative, and carbon negative. If we look at the bottom row, we have oxygen negative, oxygen negative, oxygen negative, oxygen negative. So sometimes when we're looking at the atom, the carbon negative, we should also think about its resonance, right? So here what we have is not just a clear carbon negative to oxygen negative, but it's important to think about the fact that we actually have resonance between two oxygen negatives, right? And on this one, we have the resonance between a carbon negative and an oxygen negative, right? So therefore, in comparison of these, the carbon negative, oxygen negative pair is going to be less stable than an oxygen negative, oxygen negative. But there are cases where potentially you could see an oxygen negative, think it's an oxygen negative, and it actually would have a resonance structure that would have a nitrogen negative or a carbon negative of that. Because of that, that would actually destabilize that resonance contributor. Okay? Not many cases, but there are some. So therefore, this is going to be 4. Because we're dealing with a carbon negative, right, and an oxygen negative. Now, all of these had resonance, right? But the resonance on the last one was between a carbon negative and an oxygen negative. If we look at the other 3, we have oxygen negative to oxygen negative, right? So we have the resonance, those are all the same. Then inductive, I have a chlorine and I have a fluorine, right? So that should have an inductive effect. If we look at our fluorine, this one is in the alpha position. And if we look at our chlorine, this one is in the beta position. So if these were both chlorines, right, the chlorine would have a, that's in the alpha position, would have a higher impact on the electronegativity than the beta. Okay. But we're not dealing with the same, right? We're also dealing with 2 different electronegativities. What's the electronegativity of fluorine versus chlorine? Fluorine is the most electronegative atom, right? So it's got a higher electronegativity than chlorine. So here we're dealing with both a electronegativity difference in inductive, and we haven't really talked about that yet, but the difference between a chlorine and a bromine could, if they were both in the alpha position, would make a difference, right? The chlorine is more electronegative than the bromine. So therefore the chlorine would have a bigger stabilizing effect than the bromine. Here, the fluorine has a more electronegative and it's in the alpha. So both of those say that it's going to have a bigger impact than the chlorine, which is less electronegative, and in the beta, it's further away, right? And inductive effects decrease significantly over space, right? So therefore, when we look at that, that's going to make this the most acidic, right? Because of the inductive effect. This one is going to be next, and then the one without any inductives will be third. Yes. Yeah, so even if I was looking at if we're looking at these 2, this one's going to be more acidic than that one. And if we look at the one, this is still more acidic than this one because the fluorine is more electronegative. Right, so it pulls more electron density to itself. So therefore it has a bigger inductive effect. Okay. Yes. In that case, you would have to scratch your head a little bit more. The fact that it's fluorine, the beta would have, right? And you would actually have to probably do a little bit of calculation to verify that. Experimentally, the fluorine has the bigger impact. The more questionable one, and the one that you probably won't see because it's one that you really have to go look at the experimental data, would be the chlorine and bromine. Okay, So the difference in electronegativity between the fluorine, chlorine, and bromine, there's a bigger difference between fluorine and chlorine than there is chlorine and bromine. And then there's even a smaller difference when you go from bromine to iodine. Okay. So therefore, comparing alpha of a chlorine to a beta, alpha of a bromine to a beta of a chlorine is going to be tighter. I would probably go with the bromine, but I to really get that, I would go look up the actual acidities of those two compounds. Okay, questions? All right, let's finish some reactions. This is one that has thrown students off in the past, is just, finish the reaction. So show the products of this reaction. Okay, the first thing I would do when I look at a reaction like this that's drawn out this way is to recognize that I have a group 1 metal, right? So that's my sodium. Sodium is going to be, sodium and lithium, potassium are going to be positive, right? They don't make covalent bonds, they make ionic bonds. So therefore, whatever's next to them is going to be negative. So therefore, I can convert that first molecule into this. This sometimes will help you get started. Because it's putting it in a position that you kind of understand. At this point, what is that sodium? Is that sodium an active participant in this reaction, or is it a spectator? Okay, it's a spectator ion. This reaction would more or less go the same whether that was a sodium, a potassium, or a lithium, right? The only difference would be the physical properties of the starting material, melting points, boiling points, so forth. But as far as the reaction, the important parts here are going to be the acidic proton here and the anion there, right? So if we drew the reaction of this, and you don't have to do this to complete this, but this is a good way to show the products of reactions, is go ahead and show the mechanism. So the negative is going to go to the positive, right? So the base is going to extract the proton, and then the leaving group is going to leave. So although this is an acid-base reaction, we can use the terminology nucleophile, electrophile, leaving group, right? The electron rich attacks the electron poor, right? We know it's electron poor because it's hydrogen. It has no ability to keep its own electrons, right? And then the chlorine. So the result of those arrows is I've made a bond between the oxygen and the hydrogen, and I've given electrons up to the chlorine. And what have I not, what has not been involved in this mechanism? The sodium, right? The sodium's just out there. So where is the sodium going to end up in the product? Well, why is the sodium next to the oxygen negative? Because it is oxygen negative, right? So therefore, where is the sodium going to end up in the product? Next to the negative, right? So therefore, that just floats over here. And since that has positive, right? So I could draw this as sodium chloride. Now, if we look at this one, let's take this another. I just asked you to finish the reaction, but let's take it further. Is this reaction going to proceed forward or is it going to proceed backwards? If we look at it, it's going to proceed forwards, right? Because what am I actually comparing here? I'm comparing, oops, that's a horrible color. Right? I'm comparing this oxygen negative with the chlorine negative. Now, again, we look at atoms, which is more stable, a halide, like a chloride ion, or a bromide, or an oxygen. The chloride ion is going to be more stable, right? So since this side is more stable, right, I go towards the more stable side. We haven't talked about it, but again, it's good for you to know. I put that chart on there. If we look at our pKa's, what's the pKa of the carboxylic acid? Well, it's going to be about 4.8, around 5 to 6, right? This one happens to be acetic acid, is 4.8. Okay, what's the pKa of HCl? Well, I think it's -7, right? Somewhere between -7 and -10, right? So which direction do we go if we were looking at pKa values? We go to the higher pKa value because that's the weaker acid. Weaker acid is the, right? This is the more, I'm sorry, that's the more stable conjugate base. This is the weaker acid. This is the stronger conjugate base. Okay, so the way these work is the stronger acid results in the weaker conjugate base. Right, we always go from stronger to weaker, right? We're going to more stable. So this is going to go forward. So both based on the stability of our anions and our pKa values, we get the same thing. And again, it's good if you know your pKa values, and it's a good way to learn your pKa values is to look at those, right? And again, we're looking at relative ranks in pKa values. Getting them exactly right is not essential. Questions about this one? Okay, need to work a few more of these. Okay. Okay, this one you're going to think a little bit about where your acidic proton is. So if we look at breaking that down, let's go ahead again. We got the potassium there. It's always a good idea. You could have simply just drawn it on the molecule. I'm redrawing it. The carbon is negative. The potassium is positive, right? Sodium, potassium, lithium. We have to watch that series. I've also noticed over here on this side, I've gone ahead and drawn a CH3. Why did I draw a CH3 here? I don't have to. This is actually correct, right? But whenever you end right there, by convention, by definition, that is a CH3. What do you think some students do? They all of a sudden mistake that for a hydrogen, right? So therefore, I like to kind of just go ahead and throw CH3 there, right? This is a CH3, but putting it here really will keep you from making a big mistake, or a mistake that you find later is silly and you get upset with yourself. So don't get upset with yourself, just draw CH3. So if we look at this species, the question is, where is my acidic protons? And so let's draw in those protons. And if we think about it, all the protons are carbon-hydrogen protons, and they're all sp3, right? So if we had a double bond or a triple bond, we could say, hey, the triple bond is more acidic. Here, they're all sp. So we've gone from atom. The question is, do we have any resonance or inductive effects? Okay, there's a very small inductive effect between the oxygen and the carbon here. But the bigger impact is that that could be in resonance, right? So this is a alpha position, right? And if we draw the resonance contributor for that, we can delocalize that into here. So now I not only have a carbon negative, it's resonance with an oxygen negative, right? So that's going to make that much more stable than the potentially isolated sp3 carbon. So the pKa here and the pKa here are about 50, and the pKa here is around 22 to 25, right? Because we're going from an oxygen negative to a carbon negative. Now, remember when I said a carbon negative oxygen negative is less stable than oxygen to oxygen, right? It's not less stable than everything. You have to think about what it's being compared with. What is it reacting with? What else is there, right? So this idea of absolutes, you need to lose that one, right? I know absolutes right now are very popular, but you need to lose that one, because what you always need to think about is this more or less stable? Is this more or less reactive than the other thing it's looking at? And in this molecule, right, what we're comparing it against is not a resonance between oxygen and oxygen negative. What we're comparing it with is these two. Let's go ahead and show them so you know what I'm talking about. Would be that isolated sp3 carbon and this isolated sp3 carbon. Okay, so I'm going to redraw all that so we can, and I'll go back to black. That'd make a good song. And I'm going to go ahead and show my hydrogens. And again, I like to do the mechanism. It's good practice. Drawing the mechanistic arrows are always a good idea. Okay, so the negative will pull that proton, and these electrons will go back to that carbon. That'll give me the CH3, CH2, CH2, CH3. Right, I've made a bond between the carbon and the hydrogen, and then that's going to give me negative, right? Okay, what if you went up and looked the key up and you saw this is the answer? How do we get from here to there? Okay, this has resonance, right? So this can resonate to there. And if I was going to represent the more stable resonance contributor, which one would be more stable? The bottom one with the oxygen negative showing, right? And then it is, I've got a potassium positive, it's a spectator, but I can't forget about it. It goes somewhere and it goes next to whatever's negative, right? It's just floating around until it finds something negative. Yes. This is the more stable one, but up here, right, that have been, you could have shown that as the product too. On a free response, I would have answered, I would have taken either one as correct, right? What you'll see represented most often in literature, and if it was a multiple choice, would be the oxygen negative product. And I drew this wrong. It should have been plus. Okay. Questions about this one? Want to look at one more of these? This one a little harder than. Okay. Let's try a little bit of a different one. Okay, on this one, for the carbonyl species here, this ketone, there's not really anything to redraw. It's not like we have a sodium or potassium and we need to show the positive and the negative, but it does have a lone pair and that's going to be important. So I've redrawn it with a lone pair. For the H2SO4, this is a strong acid, right? This is sulfuric acid. This is one of the stronger acids we have. I've gone ahead and redrawn that so that we can follow what's happening and so that we can compare the products when we're done. So if we have a lone pair, that's available electron density. Over here, I've got an acidic proton, right? So lone pair is going to attack. So in this case, the carbonyl is my base, right? Going to pull that proton, electron's going to go to the sulfonate. That's going to give me the protonated carbonyl, right? Plus then the oxygen negative on the sulfonate, the hydrosulfonate compound. if we look at our values here, will this reaction go forward or backwards? On this one, it's a little bit harder to think about because it seems like we're going for two species that look really stable to two species that don't look stable, right? But if we look at our pKa values, right, the pKa value here is going to be, I think it's -5, -10. It's going to be negative, right? And this one is going to be, it's either going to be -10 or -5. So let's put -5. And then the pKa here is actually around 1. Okay. And we can find that in the chart, right? What's happening here is that sulfonate anion, that hydrosulfonate anion, is really, really stable, right? Its attraction to that proton is really low. And if we think about it, that oxygen electron can go all the way through the molecule. And the molecule actually is very stable with the electronegative. It's actually one of the more stable species. That's why sulfuric acid is such a strong acid. And so therefore it can protonate almost anything, right? It's got a negative pKa, so therefore it can protonate almost anything else. And so the pKa of 1, right? And we know it's near 1. What if we didn't know the protonated carbonyl? Well, what's the protonated water? Well, the protonated water is about 0 to -1. So we know that's around 0. So the protonated carbonyl should be somewhere around 0. Okay. So again, this is going to go forward in the reaction. Okay. Questions about this one? Now, the nice thing about strong acids is there's not a lot of them, right? So we got sulfuric acid, we got hydrochloric acid, hydrobromic acid, hydroiodic acid. You can say hydrofluoric acid, you're not going to see it react much. Hydrofluoric acid has the problem of etching glass and being quite reactive to almost everything it comes in contact. So you don't really see that one much, not because it's not a strong acid, but because hydrofluoric acid is difficult. A friend of mine, they use hydrofluoric acid to clean petroleum crackers. So if you don't know what, so if you take a high, so if you think about commodity petroleum, you have petroleums that really have high carbon counts. So if we think about it, gasoline, right? We can sell gasoline for a lot of money. Then we get to diesel. That's not bad. We can sell diesel for a lot of money. People burn it. But when we get to asphalt, right, there's kind of a problem. When you get to asphalt, all of a sudden, you're not going to, it's not like everybody goes and buys asphalt, puts it in their tank, right? So it is valuable, but it's not as valuable. Nowadays, it turns out asphalt is slightly more profitable than gasoline, but that has to do with the type of crude that comes out of Saudi Arabia. So what they do is they crack it. And what crack it means is we take a carbon that's maybe carbon 20 to carbon 24, that's going to be asphalt, and we can crack it into things that are smaller, so gasoline. And we can take smaller ones like 6 or 7s and end up with propene, right? And propene makes isopropyl, propenes can make polypropylene, right? We can turn it into isobutene, which makes a rubber, right? Artificial rubber. We can turn it into enes. We can crack it. But when you crack it, it really makes everything dirty. So if you think about this, it's more or less spending a whole lot of energy into just forcing a molecule to break up into a bunch of stuff with a catalyst, which more or less, if you think about really thick oil getting burned at high temperatures on a catalyst, it doesn't take long for that to, imagine what would happen if you took a frying pan and threw oil in it and just turned it on high and walked away, right? It just coated with crud. So they used hydrofluoric acid to clean these. So it was inside of a building because the cracker was inside a building, and they were going to clean it with a tanker of hydrofluoric acid. Well, hydrofluoric acid will react with bone, so it's incredibly dangerous. So all of a sudden the pipe burst and the hydrofluoric acid started coming out. And so they ran out of the building and shut all the doors and windows, right? And when they came back in, everything was shiny, shiny silver metal because hydrofluoric had eaten everything. It had eaten all the paint, it had eaten all the rubber, the tanker, the 6 to 18 wheeler that was in there. Just imagine it being the prettiest shade of pure metal you could see. Everything had been reacted, and everything now was, you know, iron fluoride. And so it was all almost like silver, the whole thing. But anyway, so you won't see hydrofluoric acid much because we don't like to use it because, you know, it's incredibly dangerous. If you get hydrochloric acid on your hand, you can wash it off and you're probably not going to have any problems, right? You can let it sit there a little while until it hurts and you can go wash it off and you might have a red bump for a day, right? Hydrofluoric acid, if you get it on it, it's not going to feel it because it actually doesn't react as fast with organic molecules. So it'll actually soak through your skin until it gets to the bone. When it gets to the bone, it's going to start reacting with the calcium carbonate in your bone. At that point, it's really too late. And the bad part about calcium fluoride, it makes calcium fluoride, and calcium fluoride won't allow the bone to grow back. So I don't know why I got on this tangent, but there's only a few strong acids. And what you have to think about strong acids is they're negative. Almost every other organic molecule is going to be positive. So therefore, they're going to protonate almost everything. Okay, let's look at one more. We have time. Yeah, let's look at this one. And this one, I want you to show me the mechanism. So draw me the mechanism for this one. So I'll give you what the product is going to be. You draw me the arrows. Okay, on this one, right? So we have our base here, right? We've got a negative nitrogen. It's going to be really reactive. If we think about the pKa value here, it's about 35, right? So therefore, its conjugate base is going to deprotonate lots of things, right? The conjugate base of a high pKa value is going to be a strong base, so therefore it'll deprotonate, pull the protons off of anything below that. Here on the other side, we have this species with an sp3 carbon and an sp carbon. We think about those two, we have to go past the atom, right? They both end up being carbon negatives, and we have to go down to orbitals, which is our last one in our ARIO acronym. And so if we think here, sp is going to be much more acidic than the sp3, and we know the pKa value for that one is around 25, right? So we have a 35 to 25. Drawing the arrows, we're going to draw from the anion, right? The negative to the proton, and then the electron can go back to the carbon. Now it gave us the product, so now we just need to verify. Okay, I've made a bond between the nitrogen and the hydrogen. That's what this arrow means. I'm making a bond between here. And again, if you're a verbal learner, if you like to read things and you recall it for days and days on end, then what you should do is tell yourself a story every time you do this, just like Anne. This electron's going to that proton, that's making a bond. Do we have a bond? Yes, we have a bond over here. Then these electrons are going back to the carbon, right? Do we have this carbon with more electrons? Yes, we have that carbon with more electrons, right? And so this is how we go through those resonance contributors. Okay. Questions about that? Okay. All right. On Tuesday, we'll do a little bit of practice on Lewis acid-base reactions, and then we'll move into the next chapter. Okay, so if you're on your reading, we're going to do a little bit more on Lewis acid-base reactions on Monday, kind of like we did today. Spend 15 or 20 minutes just doing some practice problems, and then we'll start into substitution. So if you want to start reading the substitution chapter, please feel free. Okay, we'll see y'all on Tuesday. Remember, there's homework due Monday night at 8 o'clock. Monday night at 8 o'clock. We got office hours at 10 o'clock today. Yeah.